this is Junichiro Horikawa, and this is the 16th episode for VEX for Algorithmic Design series. And today's topic is geometry functions for VEX scripting in Houdini. Now let me first talk about the outline of today's session. First of all, I'm going to talk about how you can add geometry using VEX, and then talk about how you can delete the geometries like points and primitives. And then I'm also going to talk about the relationship between the points, primitives, and vertices using such functions like primitive, prim points, point primitives, and so on. So let's call it geo relation. Okay, and then I'm going to talk about more functions that you use in daily basis, like nearpoints and the other things, minpos and probably intersect. And finally, talk about neighbours. Now these are the essential functions that you use in VEX, in Houdini, in daily basis when you are dealing with algorithmic design. If you want to modify geometries using VEX, knowing these functions is pretty essential. So that's what I'm going to talk about today with some examples. Okay, so let's start by talking about how you can add geometries. First of all, I'm going to show you how you can add points using VEX. Okay, so I'm going to create a geometry node first, like always. And inside, let's start by creating a attribute wrangle and set it to detail. And let's name this at point 1. So I'm going to show you two examples how you can add at the point. The first example is going to be really easy. I'm going to show you how you can use the function in order to add the point on a space. If you go to the VEX functions documentation page and search for add point, you'll be able to see this add point functions and how you can use this. And there are mainly two ways to use this. One is to use a geo handle with the point number as an integer, and one is to create a point geo handle with the point positions. Now, most of the cases for the geo handle you use 0, so you don't need to really think about this one. For the second parameters, I always tend to use this second parameters a lot to determine the position where you want to add the point. Let's use this one. Since the first parameter one will just copy the existing point from the specific point number. Okay, so let's go back to the Houdini, and if you look at the output as well, it will give you a integer as a result, and it returns a point number for the created point. So right after you have created the point using add point, you'll be able to get its specific point number created by this one. So let's see how it will look like. Okay, so let's create an integer pt as a variable and call a function at point. Now the first parameter is the geometry handle. It always be 0. And then for the second parameters, you type a vector value. You input a vector value where you want to create a point. So let's say 0, 0, 0 for now, in the center of this space. And as soon as you did it, if you have set the run over to detail, you'll be able to see a single point created on the space at the 0, 0, 0 position. And let's check the position of its point by looking at the geometry spreadsheet as well. So go to the inspectors geometry spreadsheet and looking at the point attribute or point geometries, you'll be able to see 1 point where the position is 0, 0, 0. and the point number is 0. So the point that I have just created should be equal to 0. This int pt should be 0. It's equivalent to this number here. So let's also check that by setting some attributes to the one that I have just created. So let's say number to this pt that I have created with the pt as a value. So this is the point number where I want to set the attributes, and this is the value that I want to set as a value. Okay, so as a result, you get number equal to 0, which is equivalent to this one right here. Okay, so adding points is pretty simple. This is the most basic way you can add the point. Now let's make it a bit more complex by adding several points all together at once. Okay, so in that case, I'm going to use a for loop. So add another attribute wrangle, set it to detail, and this time, let's say I would like to create a points placed on a spiral like column. Okay, so to do that, first I'm going to create some angle values, how much rotation I need for each point. So let's say I'm going to create a parameter called ang, and let's multiply this by pi, which is equivalent to 180 degrees. So by setting these sliders from 0 to 1, you can control the angle between 0 to 180 degrees. Now let's set it to 0.1 for now. Oops. 0.1. Okay. Now I'm also going to create the step lengths of the how much it should be moved, how much the point should be separated. Okay, so I'm going to name it as float step length, and let's say I'm going to create another parameter called length. Let's promote this as well. Let's give 0.1. Now let's try to create many points using for loop. So I'm gonna set another parameter like for the integer using chi with num, name num. Okay. And let's also promote this. Okay, now let's give a range to this number a little bit more. Okay, and let's set the range from 0 to 100. Now I can run the loop until the number I set here. Then I would like to create some point position to create a spiral using trigonometry, like we done last time. Okay, so for the x and z value, I'm going to use cosine and sine, and for the y value, which is going to be the height, I'm just going to use this I value. Okay, so for the x value, let's write it here, float x is equal to cosine I multiplied by angle, so that the angle will be incremented by this ang variable together with this I. And then for the z value, it's going to be sine I multiplied by ang as well. And then for the y value, I'm going to say I multiply by 0.1. Okay, and let's create the vectors using x, y, and z, and then finally multiply this by a step length to control the size of the spiral. Okay, now I am going to create a point using this position that I've just created. Making just a vector value doesn't make any points, but in order to make a point geometry, you need to call this add point that we have just tried. Okay, and the second parameter, what will be going to be the position that I have just created. And as a result, you'll be able to create a bunch of points on top of a spiral curve. And if you change those parameters, you'll be able to change the shape of the spiral curve. And the numbers for the for loop will indicate the number of points being created. So for each loop, new points being created as a PT, and as as the point being created, the point number incremented by 1. So if you go to the geometry spreadsheet, each time you create a point, you'll be able to get these different point numbers. So one fact that you need to remember, that if you add a point on top of an existing geometry, you will never get a duplicated point number. Okay, so every time you create a new points, you get a unique point number, which is incremented by 1, starting from 0. Okay, so that was how you can create a point using VEX, using this add point function. Let's rename this to add point 2. Now, next thing I would like to try out is how you can create a primitive such as Polygon or Polyline. I'm going to start by showing you how you can create a polygon, meaning a faces, a primitive faces, which is created by a bunch of points with a face, a polygonal face. Now, in order to create a polygon, you first need a bunch of points to connect those points together. You need at least 3 points to create a triangle shape. And if you have, it's okay to have more than 3 points to create a polygon, but at least you need to have 3 points in order to create a polygon. So let's start by creating 3 points first, then try to connect those points together to create a triangle shape. So I'm going to start by creating another attribute triangle. And let's name this add poly 1. And let's set it to detail. Let's first create 3 points to make it a triangle. Now what I'm going to try to do is to create a similar looking triangle created by this circle node, making it as polygon, set the dimension or division to 3. So I'm going to create similar to this one. So this triangle is created by 3 points, which is on top of this circle. So if you remember from the trigonometry session, in order to calculate these point position, you can use a cosine and sine combination, just like we did for this spiral. So I mean right here. Okay, so that's let's try to do that by creating 3 points, and at each angle of the triangle is 120 degrees. If you divide 360 by 3, it's 120 degrees. So use that information to create 3 points, which is on a circle, to create a triangle. Okay, so first of all, I'm going to set a base angle, which I can control using as a parameter, and let's multiply by pi, maybe multiply by 2 as well, so that the range, if the angle range here is from 0 to 1, then the whole range of the multiplication will be in between 0 to 360 degrees. Okay, now let's create 3 points. The first point that I'm going to create, let's name this PT1 as a point number and add point. Okay, so the first one, I'm going to create a vector using a cosine for the x, and y I'm going to set it to 0, and z for the sine. Now inside the cosine and sine value I need to input the same angle, so I'm going just to input this angle as the base point value. Okay, now I am not going to multiply this created vector with anything, so that means the radius of the position of this point is 1. So I'm going to create a point on the circle, the radius of 1. So let's see how it looks like. Now that I have point right here, which is a bit far off from center, which is around the distance between the center and the point is 1. And if I move this, if I change this slider value, which is the angle, you see that the point is rotating around the center like a circle. Okay, so what I'm going to do next is to create another 2 points 120 degrees rotated from this point using 0, 0, 0 as an axis, and 240 degrees rotated from using 0 as an axis. So let's create the second point, pt2 at point 0 set. Now I'm going to use the same cosine and sine function for the x, y, and x and z value. And for the first, the angle should be the current angle plus a 120 degrees. And inside VEX, you need to use radians. So I'm going to convert 120 degrees to radians. Okay, so do the same for the z. I'm just going to copy all the angle value here and paste it inside a sine, inside a z value. Now the second point has been created. If you rotate it, both of the points will rotate it equally, but the points between 2 points is being separated by 120 degrees. Now let's create another one. I'm just going to copy this one. And let's name this PT3, and the separation should be 240 degrees now. So 240 and 240. Now you have 3 points. Load I did all together. Now what I want to do next is in order to create a primitive out of these 3 points, I need to connect those 3 points in an order to create a polygon. And in order to create a polygon, there is a function for it, which is called as add_prim. If you search for add_prim function, there's a function called add_prim here inside of VEX functions page, and you'll be able to see a bunch of parameters that how you can use it together with some description. And if you look at some of the parameters, you have at least a geohandle, which is always 0, and you have type on the second parameter. If you look at all of these, you always have this type and geohandle. If you, the type here, if to know what this type is, this is the part where you declare what kind of primitives you want to create. And there are actually several types of values for this type. If you go down to this documentation, you'll be able to see a bunch of types you can use. One is poly, which is the most used one to create a closed polygon. And another one is called Polyline, which is create a line-based primitives, just connecting the points with a curves. Now, as an additional parameter, you can also set a initial point numbers, like could be single point, could be set 2, 3, or 4 points to set initial point values, or you can also set a point array values as an initial setup. By having those initial point numbers, you'll be able to instantly create like if you have 3 points, you can instantly create the triangles. If you have 4 points, you can create squares. And if you have multiple points, you have multiple number points connected all together to create like a complex polygon at the same instantly. But you can also add those points later if you have just created the polygon using add prim without declaring any points. You can still add the point using other functions called as add vertex, and I'm gonna show you later how you can use that as well. But for now, since we already have 3 points being created, we can use, I think we can use this parameter add prim geohandle type and pt0 to pt1 and pt2, which you need to input 3 points to create a triangle. So let's try to use this one. Now also, if you look at the output it creates using these functions, it gives you a integer type. And if you look at the returns, it gives you a primitive number for the created primitives. So after you have used this, you are able to create the primitives, and as an output you'll be able to get the newly created primitive numbers, just like the point. Now let's try to use this. So let's name the variable like poly as an integer and use add prim with a poly as a type name and pt1, pt2, pt3 to connect all those points to create a polygon. Now I have just created a triangle shape, a triangle polygon by connecting those 3 points. And by rotating the points, you'll be able to rotate the whole polygon as well. Now one thing you might want to remember that whenever you want to control or transform the primitives like positions, scaling, or rotation, you need to access to its point information, which is creating this polygon, and do the rotation or scaling or translations, just like I'm doing it right now. There is actually a way to transform the whole primitives to transform if it's packed, but if it's not packed, then you have to access to each of the point, creating this polygon to control, to deform. Now that we have created a simple polygon using add prim, let's try to create a bit more complex primitives or polygon using the same functions. And this time I would like to try to create a cone shape. And if you look at the primitives of the Houdini, we don't have a cone shape here, so it does have some meanings to try out how you can create this using VEX. So let's try to do that. I'm going to create a attribute wrangle, and let's name this add poly2. And same as before, let's set it to detail. And I'm going to create some parameters first. First of all, I'm going to set the radius of the cone shape using float parameter, chf. Then also let's set this height of the cone, name the parameter as height. Okay, now also let's set the resolution of the cone, how many points you want for the circle. So let's say num is equal to chi num, which indicates the number of points on the disk, for the disk. Now let's promote these and set some random values for now. Okay, now let's write some code here. Now first of all, what I'm going to do is to create the bottom disk, which can be which is equivalent to creating a circle, a primitives, like using this circle node here as a polygon. Okay, in XYZ plane. So this division is pretty much the same as this number that I have set right here. So first of all, I'm going to create this kind of shape using inside a Houdini attribute wrangle. So let's try to do that. So first of all, I'm going to use the for loop to loop through the numbers that I have set here, like this. Okay, and then since we're going to create a circle shape. We're going to split 360 degrees and divide it by this number to indicate the each point angle value. So let's name the angle as a variable, and the 360 degrees can be declared by multiplying pi by 2, and then I'm going to divide it by num. So if the number is equal to 6, then the whole calculation of this one will be 60 degrees in radians. Okay, and then I will multiply this by I, so that each incrementation for this I will be incremented from 0 to the number -1. So if you multiply this 60 degrees by I, you'll be able to get the value incremented by 60 degrees, so 0, 60, 120, 180, and so on. Okay, now that I have this angle for each point, let's create a point position using again, the trigonometry to get the circle position. So int pt add point, and use the set to create the vectors, and for the x value, it's going to be cosine angle, and 0 for the y value, and sine for the z value. And then I am going to multiply whole vector, which I've created right here, with the radius to control the size of the circle. Okay, if you look at the space here, if you look at the scene here, you'll be able to see a radius of 0.396 with the number. We have 7 points to create a circle-like shape. So if you increase it, you'll be able to get more accurately circle shape. If you create more points like this, it becomes more circular. And you can control the radius as well. Now let's set the range for the numbers to something like 100, because 10 seems a bit too small. So I have just opened the edit parameter interface and changed this numbers range. Okay, now looks good. Now I have just created the bottom disk shape with points. Next thing I would like to do is to create a point on top of this disk, which will be the tip point for the cone shape. Now if you think about how the cone should be created, first of all you have the disk, and you have the tip point somewhere around here, and create a cone shape like this. And in order to make it as a polygon, first of all what I did is to separate this disk into a bunch of points. And then what I'm trying to do next is to create a triangle, connect the bottom points, the neighboring points, and then connect with the tip points to create this kind of triangle for one side, and continue doing that for other points to create a cone as a polygon. So that's what I'm trying to do here, what I'm going to do here. So to do that, you need the points on a disk and the tip point for the cone first. And then connect the bottom 2 points, which is on the neighbor positions, and then connect with the tip point to create a triangle for one face. So let's add the tip point for the cone. I'm going to name this as CPT, and use add point. And since it's going to be on the center, the x and z value will going to be 0, and only the y value is going to be modifiable, which I'm going to use this height value to indicate the height of the tip point. So height 0, height 0 are going to be the point position for the cone tip. Okay, now that I have enough information, enough point to create a cone value, it's time to connect all these points together to create a cone-like shape as a polygon. If you think about how you can do that, you need to access one of the point first and then get the next point that's being created and then connect with the center, the CPT point that I've just created as a tip point, and continuously doing it until the end of the points. So we can guess that using a for loop makes sense, but in order to use the for loop, we need to have all those point information as a list. Okay, and currently we don't have that yet because we have created the point one by one using the number of for loops. So we do know how many points are there, but we actually don't know what kind of point number are there existed after we have run this code. So in order to use the point number that has been created using the for loop, the good idea is to store this point number into an array in this for loop, and after creating all those points, we have another for loop to access to this array which contains all the point numbers, and use that point number together with this CPT to create a triangle. So let's try to do that. So first thing we need is the empty array for the integer to store all the point numbers. So I'm going to create an array like this, empty array like this, and then use the append function for the array to store the PT inside a PTS. Okay, now if you want to check the point numbers being created, you can create an attribute for the array, for the integer array, and then let's name this as PTS and see how it looks like. So go to the geometry spreadsheet, to the detail, and you'll be able to see a bunch of point numbers as an array, which is the point number that has been created. Okay, now that we have created the array, we can now access to each of the point using a for loop again. So for int, now we can get the length of this array by saying length PTS, and first access to each of the point numbers at I index like this. Now let's say this is the PT that I have just get inside this loop. Now the next information I need is the next point number right here. So in order to get the next point number, what we can do is to increment this I value, I, which is the index number, plus 1, so that we can get the next point number inside a PTS. So let's set the name of this first point number that I got as PT1, and for the next one I'm going to say PT2, and that is at I plus 1 index. Now there is a bit of problem with this specifications declaration, because if I is at the end of this loop, like in this case a length of PTS minus 1, say the total number of the point is equal to 10, and so the last loop, the last index number for this one should be 9, because 10 minus 1 equals to 9, right? Since the index always starts from 0. And if you look at this one, then if I is equal to 9, and if you add 1 to it, the value will become 10, right? And there's actually, you cannot actually use this index 10 for this PTS because there's only 10 points. And if the index 10 means that you're getting the 11th points on the array. So as soon as this index number got more than 9, you have to reset it to 0. to start getting the points from the first index if it's looped. Okay, so to do that, what we can do is to calculate the modulus using the total number of the point. So if this number become 10, and if you get the remain of this value by when you divided the value by 10, the number of the total number of the points, then the value will become 0. So that, which means the index will be resetted to 0. So this whenever you use these additional index values to modify the I value to get the point array, the point numbers from the arrays, using this is pretty practical. I mean, you use this a lot, so try to remember this. Now that we have got 2 points, we can create a triangle using 2 points here together with this CPT points, which is right here, to create a triangle. So let's name the primitive index that's going to be created as a tree, and use @prim and set the type as poly, and start with the CPT and PT1 and PT2. And as a result, you have just created a cone-like shape. And let's set it to smooth wireframe. So this operations works for the single face, but since I'm using for loop, all those other faces are created instantly, automatically, using this code. And now if you change the number of the points on the bottom, you'll be able to create a bunch of points, make the cone more smooth. You can also set the height and the radius. So this is a bit more complex version of how you can create a primitive, but if you break down to the simple task, it's going to be really easy to understand. And most of the stuff you're going to create using VEX, even though it looks really complex, if you break down to this kind of small steps, anything will going to be really easy to create. Now that we have created the polygon, let's try to create a polyline, another type of primitives using @prim function. Now we start by creating a simple line geometry, which is created by 2 points. Now let's start by creating an attribute triangle, set it to detail, and we're going to first create 2 points. And then, same as the polygon, we're going to use the @prim to connect those 2 points together to create a polyline. So for the polygon, we needed at least 3 points to create a triangle. But for the polyline, we just need at least 2 points to create a line-based geometry. So let's try to do that. First of all, I'm going to create a first point named as PT1. Use @point to create a point, and let's set the X position to -1, and also set the height with some parameters like using H, let's say H1, and 0 for the Z value. For the PT2, I'm going to create another point using set, and for the X value I'm going to say 1.0, and for the Y value I'm going to say CHF H2, and 0, 0, 0 for the Z value. Okay, now that I have 2 points, I'm going to create a polyline using @prim 0, which is the geo handle, and the second parameter was the type of the primitive, and in order to create a polyline, you say polyline in a string. then I'm going to indicate 2 points as initial position for initial point information for this polyline. And if you do that, let's also rename this to add polyline 1. And if you do that, you have just created this single line created by 2 points, connecting 2 points to create a curve, polyline curve. Now let's also promote the 2 height value here, which indicates the y value for the PT1 and PT2. If you change it, you can change the height of one of the point to control the shape of this single line. Now the difference between the polyline and the polygon is that one of the main differences is that the polyline is the curve geometry and the polygon is a closed face geometry. And another difference is that the polyline can also be said as a unclosed polygon, and you can say that the polygon is the closed polygon. If you look at the line here, you see that the starting point and end point is not connected. I mean, it is connected as a single line, but it's not looped. But if you look at the polygon, the starting point and end point is connected as a loop to create a closed polygon. So that's also a main difference as well. And this difference between the closed and unclosed is sometimes useful to think about, to use for several operations. So for now, try to remember what's the difference between the polygon and polyline. Now let's try another example using polyline. Let's create polyline shape, and this time I'm going to try to create a spiral shape curve using as a polygon. Okay. To do that, we have already created the point array, which creates the spiral shape. So let's try to use this point array, which I've created at point 2, to make it as a continuous curve or unclosed polygon. So I'm going to copy this one at point 2 and bring it right here. And let's name this at polyline 2. Okay. Now what I'm going to do here is to use a new function to add the point to a existing primitive. The first thing what I'm going to do is to create a empty primitive by using this simple parameter. One is the geohandle, which is 0, and the type, which in this time I'm going to use polyline. And using this one, you are not declaring any point number initially, but as I said, you can add a new point to already being created primitives. So I'm going to show you how you can do that. So first of all, I am going, before going into the for loop, I'm going to create a primitive like spiral curve using at prim 0 polyline. So currently I have just created the primitive and it does exist right here, but the primitive itself is not created from any point, so visually it's you cannot really see it inside the space. Now to be able to see it, you have to add the point for this primitive. Now let's go to the VEX function page to look for the function called add vertex, and this is the function that's going to add a point, additional point to a existing primitive. To use this one, you need 3 parameters. One is the geohandle, which is 0, and prim number, which is the primitive number that you want to add the point to, and a third parameter is the point number, which is the point that you want to add to the primitive. So let's try to use this, and the place where we can use that is where we have created the point. And this is where we have created the point inside a for loop. So what I'm going to do is to, at each iteration for the for loop, right after the point has been created, I would like to add this point to this primitive. So create a new line after creating the point, and then use the function called add vertex and call add the point inside the spiral curve for this point with this point. And as a result, we'll be able to create a polyline connecting all those points together. Okay, so that was pretty simple, but there's also another way to create a similar or as the same geometry shape, which is to use the array of points together with the add prim function. So if you remember, you can use the array of points indexes for the third parameter for the add prim function. And if we want to try doing that, then we first need the array of points being created. So let's try creating the array to store all the point numbers. Let's name this PTS. Starting from the empty array, and then use the append function to add the point inside the PTS. And I'm also going to comment this out so that I don't have primitive yet. Now after leaving the loop, all the points being created has been stored inside this PTS array. Now we can start to call the add prim, start with the 0 polyline, and for the third parameter we can say PTS, which is the array of point numbers, and which gives you the same result. So either way, using this method or starting with the empty one and add point incrementally works just fine. Whichever way is fine to use, just use it based on your preference. Now that I have shown you how you can add geometries like points or primitives, let me also show you how you can delete the existing geometries using VEX. So I'm going to start by creating grid geometry by using grid node. And let's set the number of rows and columns, say 20 by 20. And also set the size to 2 by 2. Something like this. And let's try to use the VEX code to delete the points or primitives. If it's points, we're going to delete one of the points on the grid. If it's primitive, we're going to create those faces. Okay, so let's see the differences. First of all, I'm going to try to delete the points. So to do that, I'm going to use the point wrangle to access each of the point on a grid. Then let's name this del points. Now what I'm going to do is to set the radius, how much I want to delete the points from the center position. So within that radius, I would like to have all the points being deleted within that radius. So first of all, I'm going to set the radius value. Let's say rad equal to chfd. Okay, so that's from 0 to 1. And I'm going to make a condition if the length of at p, well, for each point, for each point position, you can indicate that position as a vector value, and the length of p meaning the magnitude of the vector, and the magnitude is always calculated from the center, so that means it is the radius, it is the distance from 0, 0, 0, the center position of the space, to each of the point. So that this is equivalent to that. And if the distance of that point from the center is less than this radius, then I would like to delete that point. So to delete the point, you use the function called remove point. And you have at least two parameters you have to input. One is a geohandle, which is 0, and the second parameter is point number, the point number you want to delete. Now you can also add additional parameters to this remove point, which is a 0 or 1 value to indicate if you want to delete the connected primitives as well. But most of the time I'm not going to use this one myself. So let's try using this one. So if the point distance from the center is less than radius, I'm going to call remove point. Geohandle is 0, and the second parameter is the point number. And if we are inside a point wrangle ran over the points, then we can use ptnum to get the current point number. Okay. Now activate this one, and as soon as it did, the point has been deleted. And if you have a square value or square geometry, and if only this point has been deleted, then the square primitives become triangular primitives. So you'll be able to see this kind of pattern here. So more high res rows and columns you have, you'll be able to see more circular deletion. Right? Let's make this back to 20 by 20. So that was pretty straightforward. We have just deleted the points which is in the range, in the radius from the center. Now let's try to also do the similar stuff, but in this time try to delete the primitive, meaning these faces instead of the points, and see what's the differences. Now to use the delete prim, remove prims, I'm going to use the primitive wrangle to access each of the primitive. Let's name this del prims. Okay, now the code what I'm going to write is pretty much the same, so I'm going to copy the one that I've written inside del points and paste it right here. But instead of using remove point, what I'm going to use is the remove prim. And if you go to the documentation page again, search for remove prim, this one. This time you need at least 3 parameters, and the first one is 0, and second one is the primitive number that you want to delete, which is pretty similar to the point, remove point. And for the third parameter, which is necessary to use, which is either 0 or 1, whether you want to delete the associated points to create, which was used to create this polygon. Okay, so if you want to delete the point which is from this primitive or a polygon or a polyline, you have to set this to 1. If you don't need to delete the points associated to this primitive, then you can set it to 0. Okay, so going back, we only have 2 parameters here right now, so let's set 1 to see the points which is associated to the primitives being deleted together. Okay, and let's activate this, promote the parameter, click in this part, and change. Oops, I seem to have some okay, the problem here is that I was using ptnum, which cannot be used inside a primitive ran over. If you want to get the current primitive number, you have to change this to prim num. Okay, now it's deleting from the center, and if you're using at p inside a primitive, the at p means the center position of the primitive. So in this case, the center of this square face. And if you move the sliders, you see that each of the primitives which is in the range being deleted. And since we're not deleting each of the point, the shape, the polygon is not converted into triangle, but we're just deleting the whole face altogether. If you compare with those delete points, the points where it's just deleting this point, then creating this kind of triangle shape. But for the faces, we're just accessing to each of the face. So if you delete it, then everything will disappear. Every face will disappear. Okay. Now if you, let's say if you want to delete the faces, but if you still want to keep the points, then in that case, you set this value to 0. If you do that, you see that the points has been remained, not been deleted together with the primitive, and you can still use those points for your purposes. Okay, seems like this has some okay, there you go. So either option is used really a lot in several cases. So remember what what's this third parameter means. If it's 0, you can keep the points. If it's 1, you can delete the points all together with the primitives. Now that's it for how you can delete the primitives. Let's go to the next. The next topic that I'm going to talk about is the geometry relationship, how you can retrieve the other types of geometry from one of the type of the geometry. Meaning, like if you're looking at the point, then there is a way to look for the associated primitives from that point. And vice versa, you can get the point information which is associated with that polygon or primitives. And you can also get a vertices information as well, which we haven't used it yet. So let's try to see all those associations, the relationship between the point, primitives, and vertices, how we can get those information from other types, and how we can, and together with showing some examples, the benefits of using them. Okay, I'm gonna start by creating a box. Okay, and what I'm going to do is to first try to access to a primitive using primitive wrangle and try to get the associated points from the primitive. So in this case, the primitive is those square faces, and each square faces has 4 points, right? So I would like to get those information to create some geometry using those information. And what I'm going to try here is, first of all, let's say we have this box like this, and for each faces, I'll be able to get the point number, which creates this polygon, and use those point information. I would like to make some inner window to this face and create a window shape like this. So make this part empty and recreate this polygon by 4 primitives to create this kind of window shape. And to do that, we need to access to those point numbers. And let's see how we can do that. Now I am first going to create a primitive wrangle. Let's name this prim points. Okay, and first of all, let's try to use this the function called prim points to get the list of points associated to the current primitive inside the primitive wrangle. if you go to the prim points function description page on the VEX function page, it says returns the list of points on a primitive as a integer array here. And to use this, you need two inputs. One is the geometry handle, or I mean geometry input number for the geometry. So this can be related to the input number, which is these ones. So if you are looking at the geometry from the first input, the value will be 0. If it's this one, then the value will be 1, and so on. And the second parameter is the primitive number that we're going to look at. If you are using primitive wrangle, and if you're looking at the current primitive, you just say @prim_num. Alright, so let's try to use this. So first of all, let's create a integer array variable named as PTS, and then use prim points. Now I'm accessing to the 0 input, the first input, so the value will be 0, and the primitive number is prim_num. Okay, now let's check what the value is for each of the primitive. So I'm going to create a integer array attribute named as PTS and store this PTS that I have just retrieved. If you go to the geometry spreadsheet to the primitive, you see that I have just created a PTS attribute, and each primitive has its numbers, in this case list of integers, and all of those arrays have 4 numbers inside, and these are the actual numbers, which is the point number to create the primitives. So the first primitive, in this case, let me make the guide font a bit bigger. So the first primitive, which is, okay, I guess this one right here, is related to this one, and it has a point number 1540. If you show up the point number using this one, you see that 1540 right here. So you can see that this primitive number here and this point index array is being associated together, and you can actually get information using this prim points, so, which is pretty useful. Okay, now that we have seen the association between the points and primitives, we can actually use this point information to create what we have just have just explained, the window-like shape. Now to get back to this sketch, once we know the point number, we can get the position for each point using like point function with the p attribute. Now what we are missing right now is these corner points position and numbers, which is for this window square. And we don't have this point position yet created in a space, so we need to add the new points to create this square. Then using these point information together with the existing point number to create this new primitive. And we gotta do this for a whole side. So in this case, we have 4 sides. So we need to have some kind of loop to loop through each of the faces, each of the sides. And after we have done it, we need to delete the square that we have initially had, which covers the window. So after we have deleted it, we'll be able to see this window-like faces for each of the primitive face. So let's try to create this one. Now the first thing I would like to do is to create a new point, which is inside this face with some distance from the corner. Okay, so to do that, first I'm going to access to each of the point position in a loop in a point array here, and then use that point position and connect with the center point of this primitive, and within that range I'm going to create a new point somewhere, maybe using some parameters. So first of all, let's create an array, the for loop, to loop through all the points. Okay, and let's get the PT number, the point number at the array, and get the point position using point function. Right, now that we have got the point position at the corner of the square, we can use this together with the center position of the face to create a vector value, which goes from the center to each of the point, and use that vector to indicate a new position somewhere in the middle. Okay, so first of all, the vector from the center to each of the corner can be created like this. First of all, I'm going to declare the new directional vector value. Then I'm going to do the subtraction. The position is the corner position here, and subtract by at P, which is the center of the face. And this value is going to be the vector from the center to the corner. Now, by multiplying this value in the range between 0 to 1, you can change the size of the vector, which goes from the center to the corner. So let's try to multiply this using a float value like a size, named as size as a parameter. Promote this, and the default range is between 0 to 1, so that's pretty convenient. Now we can set the size of this vector, which will be the size in between the 0 to this corner. Okay, now that we have this directional vector, we can create a new points somewhere in the middle right here by first name this new position, and by first getting this center position, which is at P, and added by this directional value. Okay, and this calculation will give you the point which is somewhere in the middle between the corner and the center of the face. Now that we have declared a point position, we can use this to add a new point. So let's name this new PT is equal to add point 0 new pos. Okay, and currently the size is 0, so all the points is at the center of the square or center of the face. If you raise this up slowly, all the points is moving from 0 position to the corner. Alright, so that looks good. Okay, now what we need to do is to connect all those points, for the neighboring 2 points on the original face and the neighboring points which I have just created. Now to do that, it's similar to what we have done for the previous one to create the cone. We need to, one of the way to do this is to have all these points that I've created inside a new array of the points. So let's do that first. I am going to create a array called npts empty array, and as soon as I've created the new points, I am going to append this new point inside an npts array, index array, integer array. Okay. Now if I leave this for loop, all the points that has been created will be stored inside as npts. Now it's time to create another loop to access all those points, but this time we can also access to the next point inside the array. So which is going to be the neighboring point. So the number of the loops is the same, the number of the points, but what are we going to do here is access each of the necessary points. So we need at least 4 points to create the side. So let's think about, we want to get, first of all, this point right here, and which I can indicate it as a PTS at I index. Okay. Now the next one, for the next point, which is going to be this one, this point here, is going to be inside a PTS, but the index is I plus 1. So PT2 is equal to PTS I plus 1. And the same for the other example, when we were creating cone, when we have this kind of looped array, we need to get the remains when this I get the end of this array, or in this end of this loop. Okay, I think I'm missing one condition here, which is divide by this PTS and get the remain using modulus calculation. Okay, and that's for this top two neighboring points. But next thing I would like to get is this point right here, which is inside is NPTS. Okay, so for the PT3, I'm going to access to this NPT3 array, and the index is, since this point has been created from this point which have this index, so I'm going to use this index for this NPTS. And for the PT4, we can use NPTS with I, since this point has been created from this point, and this point index is currently I, right? Now that I have retrieved 4 points from 2 different arrays, one is the PTS and one is the NPTS, we can then use all those points to create the polygon, connected polygon, closed polygon, using add prim. So int poly is equal to add prim 0 poly, so PT1, PT2, PT3, and PT4. Okay, it's a bit hard to see, but we have actually created the side geometry successfully. And if we change these size parameters, I think you can see that the polygons is also changing based on this point position. Right. Now, as you can see, there is a existing face, the initial face being left over, and that is covering the window. So I don't need that. I would like to get rid of it. So the last thing I would like to do is to remove the primitive at the current primitive number, which is this face right here. And we can say either 0 or 1 here, because even if I say to 1, the point is still being used by other primitives, so the point is not going to be deleted. If it's 0, that's also fine, because the point is still going to be used for some others. Okay, so if you activate it, it looks like this. And if you change the sliders, you can change the size of the window parametrically. And if I set this to 0, it's still nothing really happens. And the number of the points is 32 here. And if I set it to 1, it's still the same. That is because even if I set it to 1 to delete the point together, but if there's other primitives using the same point number, then the point is not going to be deleted. this the point is going to be deleted if the point is not being used for any other primitives. Then this works. But in this example, this doesn't really do anything. Okay. So that's how you can use one of the relationship between the primitive and points by getting the point arrays from the primitive. Now I want to, for the next example, I want to try to get the other way around, to get the primitive information from the points. Now in the next example, I'm going to retrieve the primitive number from each of the point. In this case, if we look at this point information right here, what we can get is the attached primitive values, which is this face, and this face. What I'm going to create as a geometry here is by getting the associated primitives from the points, I'm going to get the center position of the primitive, and then create a cone-like shape connecting all those points together with the corner of the points and then the center of the primitive. And do the same thing for all the points. So for this point, I'm going to connect this point with, and for this point, which is in the back, so cannot see, but looks like this. And for this point, connect with this point, and this point, and this point, things like this. So let's see how we can do this. So I'm first going to create a point wrangle, connect with this base box again, name this as point prims. Now first of all, let's see what kind of functions we can use to get the primitives from the points. So the name of the function that I'm going to use is called point prims. Straightforward. So to use this, by using it, you can get the list of primitives containing a point. So from a point, you can get associated or connected primitive numbers as a list, as an array. Okay, so you need two parameters. One is the geometry input number, and then the point number. All right, so let's see how we can use this. So first of all, I'm going to create a primitive primitive array, empty array, variable, and then call a function called point prims. And coming from the first input, so the first parameter will be 0, and we are inside a point wrangle. So we can use ptnum to get the current point number. Okay, let's also check this to sort it inside the array attribute for each of the point, like this. So I've just created the prims attribute for integer array and store this prims from this point prims. Okay, let's check this out. Going to the geometry spreadsheet, to the point geometry, there's a additional attribute called prims, and there is 3 numbers being stored in each of the arrays, each of the attributes, and let's check what those numbers are. So first I am going to check the point number by toggling this icon here. Then let's look at the point number 0, which is this one right here. Okay, and if you look at the prims, the prim number is 0, 3, and 4. So that means the primitives which is associated with this point should have a number 0, 3, and 4. And let's check that out by showing the primitive number as well. And it is set 0, 3, 4. So which seems to be correct. If we look at number 4 here, which is this one. This should be 035 and 035, so it looks correct. So as you can see, by using this point primitives, you can get the associated primitive numbers. Now that we have known the information, let's try to use this to create the shape that I have explained. Now let's first create a for loop to access each of the primitive numbers. Like we did for the points last time. Okay, and let's get the primitive numbers inside the array. And I'm first going to get the center position of the primitive using a primitive function to get the p attribute for the primitive. Now if you access to the primitive, a p attribute to the primitive, what you get is the center position of the primitive, even though you don't see this p inside the geometry spreadsheet. That the center point position is the one that you get. Oops, I guess I should say prim here. Now that I have got the center point, I would like to use this center point position to create this triangular shape or tetrahedron shape connecting the neighboring or the associated point associated primitive centers together with the corner points. So let's create a new point at this point position using add point. Now let's also show this editor up by Alt E. Okay, and after I have created, since what I'm going to create, the tetrahedron shape is pretty similar to what we have done with the cone shape. So to do that, we also need to have an array to store all those created points again. So I'm going to create an empty array again, name as BTS, then append this PT number inside the PT PS. Okay, now apply. Alright, so what I'm going to do next is to access each of the point inside the array and then connect with the current point number to create a tetrahedron shape. So again, I'm going to create a new for loop accessing the number of points, loop through all the point number, and then get 3 points to create the side of the tetrahedron. So one is PT1 from the first index, the I index in the PTS array that I have just created. And I also would like to get the neighboring point number, which can be retrieved by adding 1 to this I index, and then get the modular of the PTS, so that if it's more than the number of the total point number, then you can reset it to 0. And finally, the third point that I'm going to use to create the polygon is the current point number at the corner, so which is PT num. Alright. Now let's try to use all those 3 points to create a primitive, a polygon. Okay, so int poly is equal to add prim 0 poly pt1, pt2, and pt3, and apply. Now something had happened since the normal, the shadow looks a bit weird now. If you change this shading to wireframe, you see that within the box something has been created, but we cannot actually see it with this shaded, smooth shaded, or smooth wire shaded. That's because that's inside, so we need to delete those faces outside to see the inside. So to do that, we can use remove prim function again somewhere to delete the unnecessary primitives. And the position where we can do that is, I mean, you can do it right after these to delete the primitive, but the most effective or most easiest position where we can delete those primitives, which is on the outside, is somewhere around here. And since this primitive number is the associated primitives which we want to delete, we can actually delete the primitive right here using remove prim, like this. And maybe some of you might think if this is okay to use it right here because the primitive is still used for other points, but you don't really need to worry about it, because when you are using point wrangle or primitive wrangle, the code runs simultaneously. You can think that all those points are calculated using the current same conditions. So that means it runs on multi-threaded simultaneously. So even if you have deleted the primitive and one of the point, on the other point, on the other corner, the primitive still exists at that point. So at that moment. So you don't really need to care about the timing when this primitive is being deleted, and think about the other points operation. You can so this totally works. Now, by deleting the primitives, I can see that the geometry has successfully been created like this. All right. Now what I would like to do next is, if you look at these geometry carefully, there is a bit of problem with the created geometry, which is like these faces has a different color based on compare with these faces, which looks white and this looks gray. Now the reason is because if you show up the normal of the faces or the primitives, you see that the normal direction of each face is reversed for these gray one. It's actually facing inward, and those white one are facing outward. And sometimes this difference makes those geometry operations in a bit weird way, or if you want to relate with other kind of operations, making all these rules be the same is pretty essential when it comes to dealing with the geometrical modification. So the next thing I would like to try is to fix this normal direction of each of the faces, which is shown as gray right now, using the vertex order information. Now if you go to the geometry spreadsheet, and if you check the vertex information here, you see that there's a bunch of numbers listed, and inside the index information on the left hand side it says 0:0 and 0:1 and so on. And what the left side number means is that these left side number is the number of the primitives, and the right hand side number is the number of vertex within that primitive. And each of the primitive number has 3 numbers, from 0, 0 to 2, 0, 1, 2. So meaning each of the primitive has 3 vertices. Now actually the normal direction of the face or the primitive is being determined by the vertex order. And you can check the order by looking at the vertex spreadsheet, that geometry spreadsheet, to the vertex section. and look at the order of the point number together with the vertex number. So as I said, on the left hand side this is the primitive number, and the right hand side this is the vertex number, and there's an attribute called point num, which is the point number associated with the vertex number starting from 0. And if by checking the order of this point number, you can also check whether the face is on facing outward or inward. So let's check that visually. Let's start by checking this face 15. Now there is a bit duplicated point number right here, so it's a bit hard to see what's going on. So it might be better if we could fuse the point number, diffuse the point which is on the same position. Maybe right after creating the geometry, so somewhere around here. Okay, now we have we don't have any duplicated points anymore, so let's check this out. So if you look at the face 17, which is this one from 0 to 1, the point number is 13, 8, 5. So 13, 8, 5. So as you can see, the point is being placed clockwise to create this white plane, which the plane normal is facing outward. Now if you look at the neighbor plane here, which is 14, it's facing, the normal direction is facing inward. And if you look at the point order, starting from 13, 8, 4, 13, 8, 4, so this is counterclockwise. And if the point order is counterclockwise, the primitive normal is facing inward. So so this is how we can indicate whether the primitive end is facing inward or outward by checking the order of the vertex together with the associated point number. So by changing the vertex order of each of the primitive, you can actually change the normal direction of the face as well. So that's what I would like to do here, using a VEX code to fix the order of the vertex so that every primitive will face outward. Okay, so let's see how we can do that using a code. Right. Now, first of all, I would like to specifically create an attribute for the normal, for primitive normal, using normal attribute, a normal node. And let's set this to primitive so that each primitive will have this primitive normal attribute inside a geometry spreadsheet, which you can access now. Okay, now let's hide this out, and I am going to use a primitive wrangle, because primitive is the one that we would like to fix, and the one that has an inward normal is the one that we want to fix. So I'm going to first create a primitive wrangle, and let's name this vertex sort. Okay. Now, first thing I would like to do is to check whether the current normal is facing inward or outward. And you can do that by checking the dot product from the center of this space to the center of this plane, and calculate the dot product between the normal of this primitive. Now let me explain in a sketch. So currently we have a boundary box like this, and there's a center here, and we have created this tetrahedron shape, connect something like this. Okay, and Each of the face has a normal direction, either this way or this way, inward, outward. Okay. Now, what we want to do is to, first of all, from the center of the space, center of the box, I'm going to create a vector going into the center of the primitive, and also have this normal attribute. Having two vectors together, we are going to calculate, let's name this V, and I'm going to calculate dot product between the V and N, and we can kind of estimate that if this is positive, then this normal is facing outward. If the dot product is negative, then we can kind of assume that this is going inward in this case. If it's going this way, the angle between the two vectors is going to be less than 90 degrees. So in that case, it can be determined as inward. If it's more than 90 degrees, then we can say this outward. So that's kind of a basic rule to get the conditions. So let's see. Let's write that in code first. Okay, so first of all, I'm going to create a directional vectors going from the center of the box, which is 0, 0, 0, to the center of the primitive, each primitive. And the center of the primitive is P, and if I subtract by a 0, 0, 0, you just get P. And I am going to normalize this to make it as a unit vector. The size of the vector will be 1. Now I'm going to calculate the dot product using dot function between the direction that I've just created together with the normal direction of the primitive. Okay, now if it's positive, then the normal direction is going outwards, so we're looking at the white one. If it's negative, then the normal direction is inward, so we're looking at this gray face. And those gray faces are the one that we want to fix. So if dot val is negative, then we would like to fix the order of the vertices. Now, in order to fix the vertex order, we first need to get the vertex indexes from this primitive. So let's do that first. Okay, so to do that, we can go back to the documentation page and look for the function which we can get the vertex index, which could be a prim vertex, or if you want to get all the primitive, if you want to get all the vertex indexes, then we can use this prim vertices. Okay, and it says returns list of vertices on a primitive. And the first parameter is the geometry input number of the wrangle, and the prim num is the second input at which primitive to get. So if you're inside a primitive wrangle, we can say prim num. Now as a return value, we can get the array of linear vertex indices in the same order as sorted on the primitive itself. If the primitive numbers is not valid, the array will be empty. Okay, so it is said linear vertex indices, which is kind of different from what we see in the vertex geometry spreadsheet. So I said that the right hand side of the primitive number is the vertex value, vertex index, but this vertex index is not actually a linear vertex index. It's a bit different one. The one we are seeing inside the geometry spreadsheet is the values which always start from 0. But the one we get here, called as linear vertex indices, is not the one shown right here, but this is the unique vertex number for whole geometry. So each of the numbers right here will be having a different value when we when it's explained as a linear index, which is actually starting from 0. So the first value, this one will become 0 when if it's explained as a linear vertex index. This one will be 1, 2, 3, 4, 5, 6, and so on. So you can say that the linear vertex index is the combination of the primitive and the vertex index, explained in one integer value, which is pretty important to remember what the difference is between this one and the linear index. And it's pretty convenient to use linear indices and linear index instead of primitive plus and vertex index. But and to use it with some other vertex related functions. So for now, remember that there's two types of vertex index. One is the one shown in the geometry spreadsheet, and one is the linear vertex indexes. Okay. Now the one that we get as a result here is the linear vertex indexes. So remember that first, and then let's get those values. So int bts prim vertices 0 and prim num. As a result, we'll be able to get the list of vertex indexes, which is the linear vertex indices. Okay, now next thing I would like to do is to get the point number associated to this vertex. And by getting the point number, you can also get the point in an order of this vertex. So if it's white one, it's on the it's on the clockwise order. If it's the gray one, you get the point order in the counterclockwise order. If you just use prim points instead of this one, you just get the point from the younger value to the older value, which doesn't really show the order of the primitive. So if you want to get the specific order of the primitive, then the vertex order of the primitive by accessing to the vertices first is necessary. Okay, so I am going to create a empty index array, an integer array called pts to store what I have found from each of the vertices. Then I'm going to create another, I'm going to create a loop through all the vertices list, access to each of the vertices at I index, and then from this vertex I'm going to retrieve the point number. So you can actually get the point number from the vertex using a function called a vertex point, just this one. So by using vertex point, having the first input for a input number of the wrangle, and the linear vertex is the second input, and we actually have that from this VTS, from this prim vertices function. So by doing it, you'll be able to get the return value as a point number associated with this vertex number. So int pt is equal to vertex point 0 bt. And as a result, you'll be able to get the point. And because I'm looping through the vertices that I got from the prim vertices, the order is always correct. Okay, now I would like to append this point number to the PTS, and then what I'm going to do is that after I have after I have created this PTS array, that point array, what I need to do is to, since this is counterclockwise, and I want to fix it to the clockwise to make this normal of the face being facing outward. So I am going to, after I have retrieved the point numbers in an order to create this inward face, I would like to make it reversed. This point order to be reversed, and use that reversed point number to fix the vertex order. So to reverse the array, to reverse the order of the array, we can use the function called reverse for the array and string. We're going to use this one here. So to use is pretty easy. I'm going to override the current PTS with the reversed PTS, which just changes the order of the point array, which will be the point order, which in the clockwise, to make this face outward, to make this face normal facing outward. Now, in order to change the actual vertices order, you need to use another function to change or override the vertices order, and that means reassociating the vertex with other point number. Okay, so to do that, there is a function just to do that, which is called as set prim vertex. If you look at the documentation page, it says rewires a vertex in a geometry to a different point. So you can reassociate the current vertex with other point. So by using the reversed point array, you can reassociate the vertex to fix the order of the vertices to a clockwise order. So let's try to do that. I'm going to loop through all the points inside a PTS array. Like this. Access to a PT number at PTS. Also access to a VT, a vertex number, a linear vertex number at VTS, since the number of VTS and the number of PTS is the same, 3, we can just use I directly. And what we want to do is associate this vertex number together with this point number, which is reordered point number. Okay, so to do that, we can use set prim vertex. Now let's check the parameter for this function. Now the first one is a geo handle, so it can be 0. The second one is primitive, and the third one is the vertex to prim, and the fourth one is PT. Now if you look at the second and the third parameters, it explains here, if the primitive is -1, then VTX to prim, which is this one, is treated as linear index. So if we don't have this number, then use the linear vertex for the third input. Otherwise, if the primitive has been specified, then this third value should be related to the geometry functions, geometry spreadsheets, this second numbers after the colon. So you can use either one, either the linear index or the primitive plus the vertex for vertex number for the primitive. Now in this case, I already have the linear index, which is VT, so I think I can just use it with the primitive number saying -1. But using primitive and the index also can be done, so we could try both maybe. I'm gonna start by using a linear index. Okay, and the last one is the PT, which I already have. So let's see how we could use that. Going back, and the first parameter was the geo handle, because that's 0. For the second parameter is prim number, so let's set it to -1 if you want to use the linear index. A linear vertex index is the VT right here, and last the PT is the one that we want to reassociate it with. Okay, and as soon as I did it, you can see that all the vertex order for the gray one has been reversed or reoriented to make it clockwise, and so that all the primitive normal is facing outward. All right, so that's how this works. Now let's see if I can use the primitive number together with the primitive associated vertex index instead of the linear vertex index. Okay, so set prim vertex 0. So the primitive number right here is the current primitive number from the primitive current primitive run over. So which should be prim num, and the VT one right here, the third parameter right here, is the vertex index, which always starts from 0, so we can actually just use this I value here. So let's say I, and PT doesn't really change, so let's say PT, and which gives you the same result. So using either option is fine. I tend to use the linear vertex, but if you don't have that information, then using this one also works. Okay, so this is how you can access the vertices to sort out the point order on a primitive. Now that we have understand the basic operations for the geometry, let's look at some of the geometry related functions we use a lot in daily basis when it gets to algorithmic design or other geometrical modification using VEX. I'll start by explaining one of the most used geometry related function called nearpoint. If you have a bunch of points on a space and you have points right here which you are looking at, the nearpoint, by using nearpoint you can get the nearest point to this current point. So in this case, this one. Okay, if the current point is at somewhere around here, then you can get the nearest point, which is somewhere around here, and so on. So the nearest point function is used to get the nearest point position or nearest point number from the current point position or the specified point position. So let's try to use that with some example. I'm gonna start by creating a bunch of points to search from. So I'm gonna start by creating a cube and then create a iso offset to create a volume out of this cube. And then I'm going to create a scatter node to create a bunch of points inside this volume. Let's limit the number to say 100. So I have now 100 points inside the box boundary. Right now I am going to create a single point, add node, and let's add one point here. And let's change the marker to this one, show handle, so that I can control the position of this point manually. Now what I'm going to do now is to get the nearest point from the point added from this add node by searching all the points through inside the scatter node. Okay, so I'm going to create a point wrangle, connect the add node to the first input, and connect the scatter node to the second input. And let's name this nearpoint. Now let's first look at the documentation page, how we can use the function that we want. And the function's name is called nearpoint. Okay, and there are several types of parameters you can use. First parameter is the geometry input number, either from 0 to 3. And the second parameter is either vector position value or a group for the points. And if we have a third parameter, it will be either a distance, maximum distance, or the position for the point together with the BD group. And the fourth, if you want, you can use a maximum distance. Okay, so if you use the first one, which is the most simplest one, you can just determine the collection of points where you want to search from with the input number for the wrangle, and then the second input with the point position to search the nearest position to. Okay, so I'll use the first one, which seems to be the most simplest one. If you need to filter which point to search from, you can use PT group as well, point group as well. If you want to filter it with the distance from the point position, you can also use this maximum distance. But if you don't care about the distance, the nearest distance from the point position, it's using the first one. It's not a problem. So let's try to use this one first. Okay, so first of all, I am going to search for the nearest point position close to this point added by add node from this collection of points. And then after I have found out the point, I'm going to try to create a line connecting those nearest point. So let's see. So first of all, I'm going to use a near point, and as a return value, you'll be able to get the integer value, which indicates the number of the found point. In this case, from the second input. Okay, so let's name the found point number as npt and use new point. Now the point cloud searching from is coming from the second input, so I type 1 for the first parameter, and then add p, which is the current point position from the first input. So that's the second parameter. As a result, you'll be able to find the nearest point number from these point cloud list. Now let's try to use that information to add a new point. Now, in order to add the new primitive, in this case line, you need to have this point be added to this node, but currently there's only 1 point coming out of, because it is based on this add node, which only has 1 point. So first thing I need to do is to add additional point using the position found from this point. Okay, so what I need to do is to first get the point position from this npt number from this second input. So vector npos is equal to point from the second input attribute p npt. Now that I have retrieved the point position, it's time to create a new point at this position. So int new pt is equal to add point 0 and pos. And then I'll be able to create a new point which was found from this point collection, which is closest to the point that I'm searching for. Okay, now that I have 2 points, it's time to create a line using add prim 0 polyline. pt num is the current point, and the new pt is the one that I've just created. Okay, now let's show up the point by merging those line and points together, and see what happens if I change the position of this add node using this handle. Okay, so if I move this one, you see that the position of the line connection changes based on the add node point position. It's searching for the closest point and recreating the line based on that, its position. Okay, so it does what it does. All right. So that's how it works for the nearpoint. Let's see the similar functions to nearpoints, which is to collect multiple number of nearest points. So that's called as nearpoints. So we're going to try to use this one next. So similar to what we have just done, I am going to create a point wrangle and connect this add node to the first input and scatter node to the second input. And let's name this near points. This time, if I look at the near points function, it is pretty much the same as the previous near point, the single near point function, but additionally, you have to declare the maximum distance to check the range. Since you're going to get the multiple number of nearest points, you have to kind of have some filter to get how many points or what type of points you need to get. In this case, the default parameter that you need to define is the point position as well as the maximum distance from the searching point. Okay, and if you can also declare the maximum number of points as well as an additional option, and you can also set the point group as well. Okay, so I'm going to use the first one, which is the most simplest one, and see how this works. And as a result, as a return value, will give you a integer array which contains all the found point numbers. Okay, so we can start by creating a variable for the integer array and then call the function nearpoints. And from the second input, and use the add p to search for, and then let's create a parameter to set the searching distance. Okay, and currently it's from 0 to 1 now. Now let's try to check the number of points it's inside, which is going to be inside this NPTS array. So first, let me try to create a attribute for the integer array called NPTS and store this NPTS that I have just created, and check how does this list changes by changing this parameter or slider. I'm going to open up the geometry spreadsheet on the left hand side, and currently nothing is inside this NPTS. That is because the distance is 0. But if I raise this up slowly, the number which is inside this array increases. So you can see that based on the distance from the point position, you can increase the search radius and then be able to find more points close nearby. And the order of this number is based on the distance. So then the first item will be the closest item, and when it gets to the right side, it gets more farther and farther, further and further. All right, so now that we got the list of points, let's loop through all those points and create a connected line with each of the points found with the current point from the add node. So len npts and get the npt. All right, now as like we did last time, we need to get the position first from the nearest point, and then we need to also, okay, this should be vector, and we also need to create a new point so that we can connect it as to get together with the current point from the add node to create the line. So add point 0, and pause. Now let's create the line, add prim 0, the type is polyline, and then connecting with the new point with the current pt num. Alright. Now it seems I'm only seeing one point here. If I increase this, okay, nothing seems to happen. Let me check. Okay, well, one place that was wrong was this part. Since I need to check the end position from the second input, this has to be 1. Okay. Now it looks like I have something here. So let's merge this collection of lines together with the scatter points. See how it looks like. Okay. And the center point, which have all the lines being connected, is the one coming from the add node. So if I move this, you can see it's searching, it has some radius from this point and searching for the closest point, and if it's in some range that I have set up, it's connecting as line. And if I reduce the radius here, you can make these smaller and smaller by doing it bigger and bigger, like that. Okay, so this is how it works. Now, using this nearpoints function, let me give you one practical example how it can be used for the algorithmic design purposes. One quick things you can do is this nearpoints function. You can create a you can use it to connect the closest point together to create kind of a network, line network. So let me show you how you can do that, which you see a lot with algorithmic design examples. Okay, so I'm going to create a point wrangle again. And then let's name this network. And like I have just done, I'm going to collect the nearest points from the current point with some search distance. Then let's promote the slider value. Then search through all the points inside this NPTS. Get the integer value, NPT value. Then I am going to create a line directly connecting the current point and the found NPT. Add prim 0 polyline NPT pt num. Now in this case I don't need to add new points because it's already from the first input. So you can just refer to the first input and that's it. You don't really need to add additional points in order to create the primitive. Okay, now it has to be semicolon. Now if I increase this one, slowly it creates a bunch of networks based on the distance. Okay, so it's used a lot for many cases to create this kind of network, connecting nearby points together to create a line network. But one issue with this one is that since we are searching, we are creating the points from either from this point and this point as well. So from this point, since let's say this point is in the search radius, then you create this line. But from this point is also within the search radius, so a new line is created. So if you look at it carefully, there's a duplicated line created for each of the position. Now that is a bit of problem. That means you have like duplicated lines created everywhere. Okay, so one way to avoid this, one way to avoid the lines being created in a duplicate way using this kind of method, you can check the current number, the current point number and the NPT that I found from the search radius, and check whether this is bigger or not. So let's say NPT is bigger than the point number, and if only that, then create a line. So when you compare 2 points, either one should always have bigger numbers. So when you only have the bigger numbers, create a line, and that makes the duplicated lines being gone, and just you'll be able to have a single line created. And if I do this visually, it doesn't really change anything, but if you look at the number of primitives, it became half the size. And if you look at the primitives, you don't see any duplicated numbers anymore. So it's one of the trick. If you think about how the geometry is being created, this is what you can do. Okay, the next geometrical functions that I would like to introduce is a function called minpos, which is used to project point with the minimum distance to a surface. Let me just show you a quick example how it can be used. First, I am going to create a sphere node, set it as Polygon, and let's set the frequency to 10 to have enough points. Okay, and I'm going to set the scale for this view to be 2. And I'm also going to create another geometry like Ravietoy, a sample Ravietoy geometry, and keep the parameter as it is, like this. Alright, now what I would like to do is to create, project each of the point on this sphere to this a test geometry and a minimum distance, just like you can do with the ray node with a minimum distance option for the entity points. So if you do that, it will look like this. You'll be able to create this kind of concave geometry. And what I'm going to do is exactly the same with this. I'm trying to create a concave geometry by projecting a point to the surface using a minimum distance option. And the function to do that is called minpos. Now let's bring up the point wrangle, give the sphere to the first input and give the test geometry the second input, and let's say the name of this function to be minpos convex. Okay, and in order to use the min position, if you go back to the vector function page, search for the minpos. So similar to the nearpoints, it will project it. It will find the closest position, but this case, the nearpoint was searching for the nearest point, but the minpos is actually searching for the nearest surface position. So it will, if you have a surface to project onto, then this can be more accurate. So you can use several parameters, like using with the geometry input with the point position, which is similar to nearpoint. You can also have a maximum distance option, or point primitive group, or primitive group plus a maximum distance. Now let's try to use the first one, the most simplest one, to try this out. Okay, so first of all, and as an output, it gives you a vector value, a projected point position. So let's name this minpos as a vector variable and use minpos So the second input is the surface that I want to project onto. And for the second input, I'm going to use P, which is coming from the sphere point position. Okay, now the minpos has been calculated. Let's try to override this current point position with the minpos, the minimum position, and see how it looks like. And voila, it looks just like the ray node projecting the point onto the surface, creating a convex geometry like this. And if you try decreasing the number of points or increasing the number of points, it should still work. Now let's try other example as a practice to use minpos for other purposes. I'm going to bring up the polyline that I've created previously. Let's use this polyline spiral here that I've created previously. Let's bring this up and to the right. And I'm going to create a cylinder which covers this spiral and also inside this spiral. And on top of that cylinder, I'm going to create a collection of points, and we'll try to create a minimum, try to use the minimum minpos function from that point to this polyline geometry to search for the minimum position. Now, the minpos is explained to search for the minimum surface position, but it actually can be used for the curve as well. So let's try to use it for the polyline to see that it also works for the curve geometry. Okay, so I'm gonna rename this to spiral, and I am going to create two cylinders to cover this geometry. So one is tube, and let's check the radius of this one, which can be declared by this length here. So let's copy this one and go back to here, and let's change this to Polygon again. Set the column numbers to 50, and then set the radius scale to the spiral lengths that I have just copied from here. Also, let's set the height as well. The height is actually based on the number of points multiplied by the step lengths in this case. Okay, so in this case 51 multiplied by the step lengths. So and maybe I should, and also multiply by 0.1. Okay, so I think I just need to multiply this by 0.1. Oops, not here. Maybe I have to set it right here. So lengths multiplied by 0.1 multiplied by a number of points. So this value, copy this one and multiply by, paste relative reference. Okay, and I would need to bring this cylinder up with the half size, with the half height value. So I'm going to copy this height value and then change the center Y with this copied value, pasted value, and then multiply by 0.5. Okay. Now I also want to give it an offset between the lines and the tube. So for the radius scale, I'm going to make plus 0.1, and I'm going to create another tube, and for this one I'm gonna say minus 0.1. Okay, so that I have both geometry inside and outside of this spiral curve. And if I change the step lengths based on the size of step lengths and the numbers, the tube will also changes its size. Okay, that looks good. Now I am going to merge these tubes together and then create a point on top of this sphere using scatter node like this. Let's keep the number as 1000 for now, and then I'm going to use the point wrangle node to check the closest point from each of the points on the tube to this curve using minpos. Okay, so let's name this minpos branches. And at each point, using the point wrangle, I'm going to create a branch, the closest line as a branch from the spiral curve. So vector minpos is equal to minpos, searching from the second input with that p, and create a new point at the found projected point position. Then create a line connecting the current point and the newly created point, MPT. And this is how it looks like as a result. Okay, and let's also merge these together with the spiral curve. And here it is. So if you can see that at each point it's looking for the shortest path or shortest point, the closest point on a surface, and the point that found is actually not really a point position of this spiral, but anywhere on the curve is used to be searched. Okay, so it's a bit more expensive calculation than the nearpoint function, but it's pretty useful if you have a curve or surface to search for the projected point position from a specified value. Now let's try to change some parameters, see how it looks like with the different parameters. It seems like it still works just fine. Okay, interesting. Okay, so that's another example how you can use this minpos function. All right, let's go to the next one. The next function that I would like to introduce is similar to minpos, but a bit different, which is called as intersect. For this intersect function, you can choose the direction to project the point to, which you can also do with the ray node. You specify the direction from the original point position, then together with the point position with the direction, you can say whether this direction has been touched with the surface or not. And if it touches with the surface, you can get its information like primitive numbers or UV information and so on. And this intersect function is really important in terms of geometrical modeling using coding, in this case VEX. So let's see how we can use this. I'm gonna go with this really simple example first. So first I'm going to create a sphere. Let's set it to Polygon and set the frequency to some value. Then I'm going to make it a bit transparent by setting the alpha attribute. For this one, you can access to the float starting from the capital A, alpha. And by changing it, you can change the opacity of the surface. So if you say 0.5, you have a bit translucent a surface. If you change this to 0.2, you have more transparency. Okay, let's set this to 0.2 for now. Let's also set this to smooth shaded. Okay, I'm also going to create a line which intersect with this sphere. So let's do that. I am going to set the size of the line to be 2 for now, so that it does intersect with this sphere. And let's also change the direction of this line randomly. Set. Okay. Now, so what I would like to do is to check the intersection between this line and this sphere using a function called intersect. Okay, so let's give a wrangle. In this case, I'm going to use this as a base geometry to check the intersection. So I'm going to use a primitive wrangle and connect the line to the first input to the primitive wrangle. Let's name this intersect, and the sphere to the second input to check the intersection with. Now, before we get it into the detail, let's look at the intersect function, how we can use that. So search for intersect. Here you go. And if you look at it, you can have several parameters like the geometry, the origin, which is the position, the original position, and a vector value. And the third parameter is the direction, which is to determine where it should be facing or directing. And then you have some output parameters like the intersected position or intersected point positions UV value. And there are several options to add a group or make it as a make UV as a vector or float. Okay, so what I often use is this third parameter here, using geometry, the original position, direction, and the intersected point position, and UV in vector value. I mean, you can use either one of it. Either one should work fine, but in this example, I'm going to show you with this one. Okay, so we have 1, 2, 3, 4, 5 parameters, and in order to use it, you need to first declare 2 outputs, which is the vector position, the intersected position, and the UV. So let's create that first. So vector P and UV as an empty value. And in order to use the intersect function, you also need to declare the starting position, the original position, to use the intersection and the directional vector. Now, I would like to use this, I would like to retrieve the information from this line here to check the intersection with this sphere. And in this case, the starting point of the intersection for this line could be either this point position or this point position. Now let's say this is the starting point, since it's pretty to determine which is 0, 0, 0 currently. And the direction of this line, so in that case, will be a direction from this point to this point. And the length of the direction is also important when you use the intersection. The lengths determine the line length. And this line length is also used to determine, to check the intersection. So if you used the small value for the length, small size vector which doesn't reach to the sphere of this sphere surface, then you don't get any intersected point position. So it's important that when you do the intersection, the ray and this line size is big enough to cover the surface that you want to reach to. Okay, so currently the line does reaches the sphere, so let's try to retrieve the point position and directional information from this line, which is from the first input. Okay, so the first point position, which is this one, can be retrieved by accessing to the point attribute at 0 item, since there's only 2 points for this line, and the first point is right here, 0, 0, 0. So you can just get the 0 index point number here. So the second point will be 1 in that case. Now to get the directional value, you can subtract +2 with +1. So let's name this dir +2 minus +1. Now that I have enough information to do the intersection calculation, let's do that. Int. If you look at the intersect functions, the output it gives you is an integer, which it returns the intersected primitive number. Okay, so it actually gives you a number of the face, in this case a triangle face, which touches with this line. So what you get in this case, this triangle's face number or primitive number here, which it should be, if I show this up for the sphere, should be, let me also show up the wireframe. So looks like I have 2 numbers being created. Okay, but I think this is the face number 92. So the intersected primitive number should be 92, and let's check that if that's true. Okay, so int prim, or let's say inter prim, is intersect. So switching at the second input, which is the sphere, and the position 1 is the one to start the intersection, and the direction is the ray value, and the P and UV is the one that is used to for the output parameter to be updated using this intersect. So after using this function, P and UV will be updated to get the intersected point position and intersected point position's UV value on that specific primitive. Okay, and be careful that in this case this UV value is can be used with a UV sample functions, which I don't cover in this session, but I'm gonna cover about this in other sessions or other days, other videos. Okay, now let's see. So now I don't get any errors anymore. Let's bring this interprim to a primitive attribute of this line to see what's the intersected primitive number. So interprim is equal to interprim. If I look at the geometry spreadsheet to the primitive, it says 92. So I think it has successfully been have founded the intersected primitive number. Now you have just found intersections, but what if the line is small enough so that it doesn't touches the sphere surface? So let's say the line size is small, which is somewhere around here, and so that it doesn't touch it with the sphere surface, then what would happen is that you get value -1. So whenever you get the negative value using intersect, that means it couldn't find any intersections. So we need to, when we are going to use this value, we need to use it in order to check whether the intersection has been done or not. So if interprim is positive, then that means you have found some intersections. Then only then you can do the operation with those output parameters and the intersection primitive numbers. Now, for this case, in this examples, I would like to add a new point to that intersected point position. Let's name this npt. Go to add point with the p, which p is the intersected point position. Now I am also going to set the color for this point. Set point attriv 0 ct pt with, let's set it to 100, meaning red color. Okay, now if I increase the line length, and you see the red point has been generated, and which is at the intersected point position. Now it's a bit hard to see with this single point, so let's also copy the point, copy the other sphere geometry to that point position. So I'm gonna give this as a polygon and make this scale like 0.1. Okay, and to specify that I would like to copy this sphere to this to the point that I've just created, I'm going to set the group to this point that I've created. Set point group 0 and inter pt and pt with 1. Okay, and let's use the copy to node. To move this sphere to this point, and I'm only would like to use the inter pt as the target point position. Okay, now that I have got the intersected point being shown as the sphere, let's merge all these information together: the sphere, the line, and the translucent sphere. Okay, so the red point that is shown shows the intersected point position. If I try to rotate this line, this intersected point will follow along with the line because it always shows the intersected point position. And if I make this line length smaller than the surface radius, the sphere radius, it just disappears. But if it goes more than the sphere radius, if it touches the sphere radius, a sphere surface, the intersected points start to appear again. Okay, so you can see the intersection is working correctly. Now let's try to do more practical examples using this intersect functions. What I'm going to try to do is to create a shadow of a geometry on top of a plane using this very intersect function. Now let's see how we could do that. First, I am going to create a grid node as a ground. Okay, and then I'm going to create some geometry. I'm gonna using the box as a simple example, and let's set the size for this one. Let's set the height to 2. Let's also bring the center up above. Okay, so it lands on the the ground plane. Now let me also color this box to some colors like cyan, probably. Okay. I'm also going to create a group to this ground with saying floor or ground, anything. Now, what I'm going to do next is, first of all, I am going to create first of all, there is a plane and a geometry like this, and the next thing I'm going to do is to set the direction of the light to create the shadow. Let's say I'm going to create a sunlight, right? And using this direction, I can cast a ray from each of the point on a geometry to that direction, like this. Okay, and until it touches the ground. So what I want to do is to get the intersected point on the ground with this ray, and for every point, and connect those points together, and this one as well. This point, it just touches the ground as soon as possible. Now if you connect all those points together and fill it with other colors, you can just make a shadow, just like a shadow geometry. So that's what I'm going to try to do using intersection to create a shadow on top of a ground. Okay, so it's not that hard as you think. Use point wrangle. So what I'm going to modify is this base geometry, the box geometry. So I'm going to put it into first input here. Let's name this shadow. And as a guide, I'm going to bring this floor to the second input right here. And as an additional information that I need to set a sun position and the direction. I mean, the position doesn't really matter because it's like unlimited. It's at the unlimited direction, so it's pretty much the same as the directional light that has right here. So I'm just gonna create a line, and the position doesn't really matter. I'm gonna bring this up a little bit, like 3, and then the direction of this line only matters. So let's set it to some direction like this. Okay. So this is going to be the sun direction here, and I'm going to use this direction to cast a ray from each of the point on the box and find intersection with this plane and create a shadow. Right, so I'm going to bring this line to the third input, and let's start doing the code. So first information I would like to retrieve is this directional value from the third input. To get the direction, you need to get the first point position and the second point position. So I will get that by, let's name this L plus 1, point 2 P0 for the first starting point position for the line, vector L plus 2, point 2 P1. That's the second point position. Okay, now I am going to calculate the direction of this line, of this ray, starting from this point to this point, by saying L there is L plus 2 minus L plus 1. And I'm going to normalize this first, then multiply by some really big numbers. Because as I said, in order to use an intersect, it has to be long enough to touch the grid, in this case, the ground. So I have just made it long enough for this directional vector value. Now, it's time to use the intersect function. First, we need a output parameter vector p and uv. Okay, and also I think that's it probably. Now let's create a int prim, which is, let's name this interprim, and use intersect. And the intersection has to be done with the ground, and which comes to this second input, so 1. And let's also set the group floor. If you look at the intersect function page, there should be a group value here, which says for the second parameter. Now this can be used to determine which geometry to use within the input. Now there's only one type of geometry with the floor, so I don't really need to set it as floor, but just in case, if you have multiple objects within this node, you can use group to filter out the specific geometry you would like to calculate the intersection with. Now the third parameter will be the point position to start with, which I am looking at this box and with the point wrangle, so I'm looking at each point on a box, right? So each point will be the starting point for the intersect in this case, and then use L direction that I have just calculated right here for the third parameter, fourth parameter, and then P and UV as an output parameter. Okay, now if it all succeed, if all these successful, and you'll be able to get the intersected point position right here, which should be somewhere on the ground. So what you need to do now is to just change the position of each of the box point position with this intersected point position. And as a result, you'll be able to get this skewed geometry. And if you just set this color with black, it will look like just like a shadow geometry. If you merge this together with the ground, shadow, and the box, and here you go. Now the point position, the height position of this shadow and the ground position is at the same height, so in order to reduce this tinkling here, you can raise up this shadow at Y direction a bit with a little value. So set 0.001 0. We'll raise up this shadow a little bit upward to reduce this tinkering. Okay, now that looks like a shadow. And if I try to change the direction of this line by moving this value, it does seem like it's changing its direction. And if it's too big, then if the intersections goes above, and if it couldn't find any intersection with the grid, it gives you this kind of a buggy geometry. So the limitation with this one is that the intersection always has to be within, intersection has to be found on a grid at always if you want this to work. Okay, but as long as the directional value together with the base point position is within the grid, it works just fine. Okay, so this is another example of using intersect to create a shadow. Now, one last function that I would like to show you in this section is called neighbours, and to look for the neighbour points for a specific point position of point number, and which is also a really important function in VEX in terms of geometrical operations. So let's see how we can use that. We're going to try this neighbours from the simple example first. I'm going to create a sphere and then set this to polygon. The first thing I'd like to do, I'm going to make it as a dual geometry by using divide node and make it compute dual. Makes this kind of circle ball like shape. Now from using this geometry as a base, I would like to use the neighbor function. Now, using a function called neighbours, you'll be able to get a connected point numbers for specific point numbers. So let's say if you're looking at this point right here, then what you get as a neighbours is this connected point numbers. Okay, if you look at this one, if you are looking at this point, then the connected point is this point. And these are the neighbor points. So that's what neighbor is, and actually that's just all. But there are many cases when you want to use this neighbors for. So let me show you one simple example first. Now for this example, what I'm going to do is to first search for all the neighbors for each of the point, and then you'll be able to get the the point information on the connected corner. Now what I want to do is to, after I have get the connected point neighbor information, I will like to get the half position between the connected position and the current position, and using that half point position to create a triangular using all the neighbor information, triangular to create a triangular shape, and do the same for all the points. And after doing it all, I'm going to delete all those existing primitives. So let's see to change the whole shape with a specific simple rule. So let's see how we could do that. Okay, so I am going to first use the point wrangle node. Let's name this as neighbors. Okay, now let's see how we can use this neighbors functions. So this is called neighbors, and by using it, you can return an array of the point numbers of neighbors of the point. Okay, so it returns the integer array, the list of point numbers, and the geometry is the input number here from 0 to 3, and the pt num is the point number that you're looking at. So if you on the point wrangle to look for the current point number, you can use @ptnum for this one. And as a result, you'll be able to get the point number of the connected points or neighbor points. Right, that's pretty straightforward, so let's try to use this. So I'm going to start by using this neighbors. So I'm going to name this neighs with the integer array variable and call neighbors function at ptnum. Now as a result, you'll be able to get the list of points, an array of points. So I'm going to loop through all the points here. And most of the cases, what you get is 3 points as a connected, as a neighbor points. So loop through all these points, neighbor points, first get the actual point number from the list, from the array. Okay, and then I'm first going to get the position at this neighbor position, neighbor point number. So using point function. So if I'm looking at this point, then I have just got the point position for this, this, and this. The next thing I would like to do is to calculate the middle point position between the neighbored point position and the current point position. So that will be, let's name this nearpoints is equal to the current point position plus a npos minus current point position multiplied by 0.5. Or to make it simple, you can also say at p plus npos multiplied by 0.5. Okay, now this is the point where I would like to create a new point. So next I'm going to give a new pt with an at point function to create a new point. This, and if say apply, and the new point has been created. Now that I have created the point, I would like to connect all these points together to create a polygon. Now you can do that two ways. One is to use add prim with the point arrays, or one is to use the add prim together with a add vertex. Now I'm going to use the add vertex way. So first I'm going to create a empty polygon value or primitive. Add prim 0, the type be poly. And then inside the for loop, I'm going to use add vertex function to for this poly to add the new point that I have just created. Now the new triangle has been created for each of the point. I think the next thing I should do is to delete the current primitive geometries. And the current primitive geometry is already associated with all the points, or all the existing point, and all the existing point is not used anymore with the new triangle. So what I can just do is to remove the point at the current point number. And that's just it. And there you go. You have just deleted the original polygon and then created the new polygon out of the base geometry with this one. Okay. And this, since this is very simple, the system is very simple, it still works for any kind of geometry. I think if you make this compute dual unchecked, it still works, but it gives you a bit irregular shape, which is because of the order of the point found for a neighbors. So when you get the neighbor, the order of the point is not always like counterclockwise or clockwise. It's a bit random, so you cannot just do add vertex in this case, but you need to find the correct order to actually create it a clean polygon. So that's kind of a reason why I converted into compute dual to make the neighbor numbers always equal to 3, so that in that case, even if the order changes, you always get triangle shape no matter the order is. Okay. So this works just fine. Now that was the simple example for the to use the neighbors. Now I would like to show you another example, a bit more complex, a bit more practical example. Okay. And what I would like to do is to first create some based geometry, maybe using remesh, and then out of that mesh geometry, I would like to retrieve the random network out of those mesh and using a neighbor function. Okay, let me explain. So let's say I would like to use a test geometry like squab. Okay. And currently the density of the point is a bit too high, so let me reduce the number of points using remesh. Okay, and let me also show up the wireframe. Okay, this might be too low res. Let's say 0.1. Okay, looks good enough. Now, what I would like to do is to, starting from a random point position on top of this mesh, I'm going to randomly pick the neighbor points. Let's say from this point, I'm going to pick the random point, neighbor point like this one. And from this neighbor point, I'm going to pick another random points, which is somewhere like here and here, and keep doing it until there's a dead end. Now, since I'm picking the point number randomly, there is a chance that the point goes back to the original point position, but I would like to reduce that as well. I would like to avoid that as well by checking the already visited point number. Okay, and keep doing it until it gives a dead end, and if it founds the dead end, then found the new random points again at somewhere which is not taken yet, and try to create the network again, the random network again, until it fills the whole squab geometry. And as a result, you'll be able to get some kind of random network running on top of the squab, retrieve it as a pattern, random pattern, polyline network. Okay, so to do that, I would need to use probably I don't really need to use the point attribute, because the things that I'm going to do is a bit more like a feedback loop, which you might have done it using a for each loop. So I'm going to try to do that using a for loop, nested loop using a detail wrangle. So I'm gonna give a attribute wrangle first, then connect this remesh as a guide to the second input, then set it to detail so that it runs once, and let's write some code. And the code written here is going to be a bit advanced than compared to the others, so if you couldn't follow it, don't worry about it. But I'm just using the same information that I've been showing you, so if you look back all the sessions that I've taught you, you should be able to understand what's going on here. Okay. Okay, so first of all, I am going to create an empty array which stores all the visited point numbers. So let me name this as cons, meaning as connections. Okay, now there's gotta be two loops. One loop is to check to create a new polyline network after it found the dead end, and another loop is to create the polyline network itself. Now let's try with the second loop to create the polyline network. So I'm going to use the for loop, starting with the really low numbers like 100 or maybe 20 or 30. when you do a feedback loop, it's better to start with the low numbers to test out, and if it looks like it's working well, then you can raise this up more and more. Okay, now first of all, what I'm going to do is to add a new point which is which is from the geometry, the squab geometry mesh. So currently the squab geometry has like 2,169 points. So what I would like to do is to get a random index within this range, within this point number range to start with. Okay, so let's create the index first with a random value, int index. First of all, I'm going to retrieve the endpoints, which is the number of squab geometry, point number on the squab geometry. Then I'm going to multiply this by a random value, and using some seed value, I'm going to create some parameter for the seed. Okay, and then probably add with some constant value. Okay, now after I got this, I am going to create a, well, let's say this is the index value. Okay, maybe I'm just gonna call this PT instead of index. This is a point number from the second input. Okay, now what I would like to do next is to check if this point is inside this cons or not. Well, actually I've started from the empty array, so it's assured that it's not inside this array yet, but later on, if we do the feedback loop, there is going to be a chance that the point is inside this cons. So let me just do this condition here at this moment. So search for the cons and use finds to check whether the point is inside the point number is inside this array or not. And if it gives you negative value, then it couldn't find. If you couldn't find a point inside the cons, then you can actually use that point to create it as a new point, right? So only then do the calculation, and only then start creating the polyline geometry. So starting with the empty polyline like this. Okay, now inside a for loop, I will, the first thing I would like to do is to append this point number that I have just created to this cons array, connection array. Okay, now next thing I would like to do is to get the actual point position from this index, from the second input. Okay, just this remesh, from this remesh. Now that is vector pos point second input. I want to retrieve the point position attribute at PT. Okay, now this is coming from the second input, so currently from the first input nothing is created. So if you check this node, no points, I mean only one primitive has been created, which is this polyline that I've just created, but no points yet. So let's create this point as a new point. Okay, then set some color to this point. Set point attriv 0 cd new pt with some color based on maybe a random again, but using some constant seed value. So let's create a color vector value using random, maybe 2-point constant value plus chf seed again. Okay, now let's give this color as an attribute to cd. Okay, now after I have created this point and set the color attribute, I'm going to add this point to this polyline using add vertex. So 0 polyline new pt, apply. Okay, at this moment 30 point has been created, but it's on the same position currently because I'm not given the next point position to create a polyline network. So what I need to do next is to search for the neighbors from this PT that I've found from the second input, and then check for the neighbors and also check if the neighbor point is already inside the cons or not, and if it's not, then use that neighbor to actually calculate get the network, or use that point as a next point for the polyline network. Okay, so to do that, I have to loop through all the neighbor values that I have found at this PT number. So let's get the neighbor list first. So int, which should be inside here, I guess. So if int npts list equals neighbors from the second input with the PT. Okay, and I'm going to loop through all the values inside this neighbors. Maybe I'm gonna use n as an add variable, then npts okay, I seem to have some index problem here. All right. Now, what I would like to do is to first get the MPT value at n. Okay. So starting from 0 until the end of the MPTS index, and what I need to do next is to check if this NPT, which is the neighbor point, is inside this visited array list, visited point array or not. So do the same like I did right here. Okay, I'm just gonna copy this one and give a condition here. If this NPT is not inside, then you can use this NPT for the next point numbers. So in that case, I can override the point number, which is this one, with a new point. And then I can also break this for loop to exit. Okay. Otherwise, you have to look for the other point numbers. You have to look for the other point numbers for the other NPTs. So maybe I don't need this Actually, I don't really need to set the conditions here. So just leave it as is. Okay. Now what I need to know next is to whether this point found, whether if I have found any point at this point or not. If you couldn't find any neighbor point which can be used, then that means you're at the dead end. Then you have to create another polyline for the next loop. So to check that, what you can do is to create some check-in integer value, like say check, and starting with the -1. And this is the part when you have found that there is a point to use for. So in that case, you can set the check to, let's say, 1. Maybe I can start with 0. And only if the check is 1, you can continue doing the loop. But if the check is remained as 0, which means you couldn't find any point to be added, then that's the timing you want to leave this whole loop to create a polyline. Okay, so the indent is a bit weird here, so let me fix that first. I'm going to... Okay, it looks good. Now to do that, do the additional condition here. If the check is equal to 0, then break this for loop right here to go create a next polyline. Okay. So for the single polyline, this function should work. Let's see how this works. And now, if you look at it carefully, so the starting point should be either this point or this point, and what it's doing here is to find the neighboring point, the random neighbor point, and continue finding the neighbor points until it finds the dead end. Well, it's not finding, there are still some options to go, so it didn't find any dead end. It just stops because of this limitation for the loop. So let's say I set the numbers to 1000, and let's see how it will create the new line. Now it stopped at this moment. I think the starting point is this one and goes up till here, and maybe when the point reaches to this point, it couldn't find the next point position because this was actually the dead end. These points, the neighbor for this point has already been taken by other points already being used, so that's actually the dead end. So after it finds a dead end, I would like to pick another random point at somewhere on this graph, which is not used yet, to create another polyline network until it fills all the mesh. So let's do that. Going back to the code, what I need is an additional for loop after I have left this base loop here, base condition here. Okay, so I'm going to create another for loop. Int, let's say t is equal to 0 until, let's say, 10 to test out with the small numbers. Okay, and let's give it an indent here. Now, what I need to do is to use this t for the random seed to pick to pick the random points for the next iterations to create the next random polyline. So I would need, I guess, multiplying t by this this value makes sense. Maybe adding by plus some constant value as well. Okay, and let's also do the same for the color value, which is right here. So multiply this by t, added by some other constant value. Okay, accept, and if you play it, you'll be able to see a multiple line being created. In this case, it should be 10 because I have limited the number to 10. Now that I have all those information being written here, I think I can increase this number to more than 10, like 1000, and voila, it has just created a random polyline network to cover all the squab geometry like this. Okay, looks like a modern art. Right, so that's how you can create a feedback loop together with the neighbors, which is one of way to use neighbors for this kind of purposes. Okay, and you can do whatever you want after this. Let me name this neighbor network, and if I smoothen out this network using smooth, you create like a more like a neon sign like pattern. It looks interesting. Okay, and if I change the resolution of this to say 0.05, I think it should still work. Now the calculation seems to take a little bit more, but the result is promising. All right. So this is it for the neighbors, with some simple example and some advanced example. Now this is it for today's sections for geometry functions. The ones that I've shown you today are the really essential functions in order to create a geometry, delete, modify, and do some analysis, get some relative information for the point, primitive, and vertices. And you're going to use these functions a lot in order to modify a geometry. So try to use them a lot in your daily basis for the coding, and you get used to it, how you can use them. Now for the next topic, I would like to talk about intrinsic values, which is similar to attributes a bit, but it's a bit more special preserved attributes, which I don't use that much, but it's also essential things you need to know about. So let me talk about that. Okay, so this is it for today. Thank you for watching, and please like and subscribe if you like the video, and if you like to follow the upcoming videos. And I have also started the Patreon myself. If you are kind enough to support me, I'd appreciate that as well. Okay, thank you very much, and goodbye.